Welcome back. In the previous lecture, we had introduced an important model for nuclear reaction. This model is called the compound nucleus reaction model. In this lecture, we will elaborate few additional features of this model. In the previous lecture, we had seen that the excitation energy is shared amongst the different nucleons of the nucleus. So it is not possible to just use the excitation energy to remove one of the nucleon. Um, so that is why even when the excitation energy is more than the separation energy, it's not possible to remove only one nucleon selectively. Um, so this excited energy, this is released eventually by a gamma photon emission. However, there is a certain feature. This is the feature which is seen for high Z nucleus. But when you look at low Z nucleus, if you remember, the separation energy decreases with A and atomic number and atomic weight, right? This is what we had seen in one of the earlier lectures on separation energy. So because of this feature, what happens is that for low Z nucleus, the proton emission and alpha particle emission starts competing with gamma photon emission. Okay, so while typically only gamma photon emission is seen for high Z nucleus when excitation energy is slightly more than separation energy. For low Z energy, this becomes more possible. Okay, so that's the difference between low Z and high Z. There are other features. So if you remember, so we had shown this a plot earlier. What you see is that there is a sudden increase in cross section at certain energy levels, right? So these resonances are, we can't do justice to dealing with resonances in a quantitative manner. These are extremely important in many areas of science, both in physics and chemistry, not just in chemical reactions, nuclear reactions, but in many other places where energy transfer occurs. So all we can say qualitatively is that energy transfer becomes much more efficient at some specific energies. Uh, Therefore, the cross section increases. Here, there is a general trend. There is a decrease in cross section with increase in neutron energy. When neutron projectile is used on silver, but at some specific energies, the cross section increases dramatically. The theory of resonances is more involved beyond the scope of this course, but typically it has a lot of information. The information on the width uh, is indicative of the lifetime of these states. You have to take a more detailed course in chemical dynamics or nuclear dynamics to understand these things more quantitatively. But all we have to take away is that it has lot of information about the structure of the nucleus and the energy levels that are present. Uh, so the theory of resonances was developed by Bright Wigner. This is used both in chemical dynamics and nuclear dynamics. This formula, again, we will not derive this at this point. There is an appendix in this book. If you can look at this book to understand how it is derived, but perhaps at a later stage we'll come back towards deriving this equation. So, but what is the formula that is being presented? This indicates the cross section for neutron projectile and gamma emission. This is the de Broglie wavelength. This is the nuclear spin of the product. Gamma photon is the other product. So nuclear spin of the reactant projectile. This is the other reactant, nuclear spin of the target nucleus. This is the line width of neutron channel, line width of the gamma channel. This is the overall line width. E is the energy of the neutron. E naught is so-called resonance energy. So right now, all these things are perhaps jargon without elaboration. But I request you to go through the appendix of this book. But Bright-Wigner formula is sort of standard in many reactions, including chemical reactions. You can look at many books which would elaborate about this formula. In any case, let's move on. Where are we going to use this? Okay, so what is generally shown is that most all these things are constants except for the line width associated with the neutron channel. The neutron line width depends upon the energy velocity of the neutron. Therefore, in addition, you know that the de Broglie wavelength is inversely proportional to the momentum of the neutron. Putting these two features together, what you can see is that the cross section is proportional to V by V squared, right? Because this term is proportional to V. This is a quadratic term that is proportional to V squared. What can be inferred is that the cross section is inversely proportional to 1 by V. So this is a feature that is seen in the experiment. This decrease in cross section with increase in velocity or the increase in neutron energy, it can also be explained via the Bright-Wigner formula. Okay, so that there is a model to explain that feature. In addition, these features of why the line width decreases as the energy increase can also be explained. There's a model available to rationalize all these features. This is beyond the scope of this course, but it is possible to rationalize these features. These are these are well understood aspects of nuclear science. So another important feature is that when you use a charged particle, accelerated charged particle, and excite the nucleus, what is seen is that the excitation energy, okay, so the follows a particular pattern. Okay, so what we are measuring here is the number of neutrons emitted at a particular energy, right? So, and why are they emitted? Because they've been excited by a charged particle. Okay. So what you see here is something like a Maxwell-Boltzmann equilibrium distribution, right? This is when you're exposed to kinetic theory of gases in your high school, you would have seen this formula. That is a formula that is used for a system at equilibrium, a gas at equilibrium. So likewise, this is like a neutron getting evaporated from a nucleus that is at equilibrium at a temperature T. Okay, so because when you measure the number of neutrons at a particular energy, you see this kind of distribution, then we can attribute something like a temperature to that nucleus. All this is supportive of the compound nucleus reaction model, wherein the projectile's energy gets equilibrated into the entire nucleus. So just to re-emphasize, this Maxwellian type of evaporation spectrum, that is, what is getting evaporated? Neutrons are getting evaporated from an excited nucleus. because of this Maxwellian spectra, we think uh, there is an evidence for the energy to be distributed equally amongst all parts and all components of the nucleus. Then, in addition, there is an angular symmetry of the emitted particle. Supposing it's the neutron that is getting emitted, there is a particular symmetry which is independent of the impact of the projectile onto the nucleus. All these things are indicative of or additional proof for the validity of compound nucleus reaction model. In the next lecture, we will go into certain other types of nuclear reaction. Thank you.